Thank you for coming to my talk. Today will be talking to you about how I use Scenic and Nerves to draw to a 7-color e-ink screen. But first, a little bit about me. I've been developing in Elixir for quite a while now. I like to use Nerves in many of my different hobbyist projects, and you can follow me on Mastodon. I'm also an engineering manager at Felt, where we're making the best way to make maps on the internet. And I'm a maintainer of multiple different Elixir libraries, such as Scenic, Inky, Xsync, Scenic Library Load, Main Proxy, and a couple others. So where are we going today? So today, this is the screen that I'll be talking about. This is what it looks like, and I'll show you more later about we're talking about the journey of how to get here. So first, why do I love e-ink? The main reason is because it just looks so much closer to paper than what LCD does once you look at it through a microscope. So you can see e-ink on the left over here looks pretty close to paper in the middle, whereas LCD is made up of all these individual pixels that are different colors that, because they're so small, your brain just makes them into one, or you can't notice all the individual pixels. I've also seen some really cool e-ink projects online. This is somebody who has a full-page view of the New York Times that refreshes every day. It looks amazing. It's really large, but the downside is that this display costs on the order of $1,500, so a little bit out of my price range for now. But I really like e-ink. I have many different sorts of displays, and yeah. So why do I love it? One of the main reasons is because it's very low power. It only uses power when you're actually drawing to the device. After you finish drawing, then the image will just be stable, even if there's no power. Also, there's a little bit less eye strain because there's no backlight that's glaring at you, and I just really like it because it's like paper, and I like paper. But let's start with some definitions here. So first off, so what is e-ink exactly? Well, it's a display technology that allows you to draw with pigments on the screen. And it does that by using microcapsules to draw little black and white pixels, or pixels on different parts of the screen. It's made up of different components, so it's all these individual microcapsules here. There's 3 I'm showing, but we'll be focusing on the middle one, but think of them each as an individual sort of pixel. And those are sandwiched between different electrodes. And so by default, you have all the different e-ink particles floating in a sort of viscous solution, and those particles are different charges and different colors. So here I have negatively charged white particles, and then positively charged black particles. And by default, they're just floating, but as soon as you apply an electrical charge to the electrodes, for example, if you apply a negative charge to that top electrode and a positive charge to the bottom electrode, then all of the negatively charged white particles will float to the bottom, and then all of the positively charged black particles will rise to the top. And when you view this system from the top, you will see a black pixel because those particles are opaque. But how does that work with multiple colors? Well, the multiple color e-ink technology that I'm using in my display here is called advanced color e-paper. So it works very similar to the principles that we just outlined, but now we're adding multiple other particles of different colors, different densities, sizes, and electrical sensitivities in. And so by rapidly changing those charges in a set of predefined patterns, you can control what the final ordering of those different particles in your microcapsule are. So here's the same system, but this time with larger positively charged red particles brought in as a middle layer. And so by default right now, those are being drawn to the top because we have the negative charge at the top. But if we flip the charges briefly, then the red particles will start to move down, but the black particles will also start to move down as well. And because those are smaller and they're more electrically sensitive, they'll move faster. And if you then remove the charge, the red particles will stay on the top. And the key is to do that before the white particles start going all the way rising to the top above. And so now, since you're viewing this from the top, you end up with a red pixel. So one of the problems with this advanced color e-paper is because you have to do that flashing multiple times to get the right ordering of all your particles, that it is very slow. And this one is actually slow on the order of 40 seconds, so almost a full minute. Other e-ink, especially just plain black and white, can be a lot faster. maybe half a second or even less if you're doing like a partial refresh. So this is what it looks like on here, and I'll do a little demo here. So there are multiple different colors. Here's the 7 different colors that we have on the display. And when it starts to refresh, you'll notice that it does an inverted version of whatever the final screen will be first. And that's so that the final, just to make it look better. And then as it's flashing here, you can see that there's some ghosting from the previous image. But then over time, as we sit through these 40 seconds, we get to this full color refreshes here. And then it's going to come in with the actual display. And different colors will come in first, and then other colors will then follow. And let's see if my, oh, this is not going yet. That might take a little bit longer. Will I just, yeah, it's okay. And so a fun e-ink fact is that these multicolor e-inks are actually temperature dependent. So there is a temperature sensor that is actually sitting on the board. And based on whatever temperature it reads, a different set of waveforms will be used for drawing. OK, continuing with the definitions. Nerves is a framework that allows you to run Elixir and Beam on top of embedded devices. It runs on build root. And you use Elixir or the Beam as the init process on the device that allows you to bring it is responsible for bringing up all the hardware. It allows you to react to events like when the network connects or when like a USB is plugged in. And another core piece of Nerves is all the scripts to build and update your firmware on the device. And Scenic is what I would call maybe the premier graphics library for Elixir. And it is targeted at embedded devices and is made by Crichton for their Crichton OS, which is a security-hardened operating system made for using the SEL4 microkernel. Check it out, it's really cool. So why use Scenic in this project? Well, the main reason is because there's no web browser used at all here. Web browsers are amazing pieces of technology, but they are incredibly complex. There's so much code that goes into them, and also they can end up being rather slow on constrained hardware such as this. But then the other reason is because by using a more low-level technology like Scenic, I can get much better control over the rendering. And what is Inky? So Inky is a series of hobbyist e-ink screens that are made by Pimoroni. They range in size from 2-inch to 7-inch. The ones on the top are only 3 colors, which actually allows them to refresh, I think, in about 15 seconds. But the ones on the bottom are a full 7-color. And the one that I'm focusing on today is the Inky Impression 7.3-inch on the bottom left. And this is what it looks like on the back. There's a 40-pin header, which is where the Raspberry Pi connects. There's some I2C connectors if you want to have a connect out like a temperature sensor. There's some buttons that are built in, which is really nice. And there's a driver chip somewhere on the board. I'm not sure exactly where it is, but that's what's actually sending the individual waveforms to the e-ink screen. So let's talk about my Inky journey. Try this one more time. So if you go back a couple years, I was hanging out on the Elixir Slack when Lars Vikman posted on there that he had bought a Inky Impression 5.7-inch display, this cool little screen. And this is the first time that I ever heard about color e-ink. And so it did not take very much convincing for me to smash that buy button and to buy it. And yeah, Lars is saying, oh, I started on process of like porting over the Python library to Elixir. So me and Jason Johnson both go ahead and buy it. But then before Lars is actually able to actually test on hardware, he has other priorities, I guess, rather than just working with e-ink. So I take over the project, and then I start digging into like the byte layout and trying to understand, how does everything work on like the data sheet? How does e-ink work? And it took a little bit of doing, but eventually I finally got something to render onto the screen. It wasn't very pretty, and there's like all these like extra bars and lines on here. And that was related to how I had to pack the bytes. But with a little bit more finagling, I was able to draw any sort of abstract art I wanted by just providing a specific color for each individual pixel. But we wanted more than this because we want to use Scenic in order to actually drive the screen so we can render our own images and text. I don't want to draw text by hand. So some time passes. I get a little bit busy. I go on a trip. Lars has a kid. At this point, Jason Johnson takes over the project. He cleans up my code because it was like super hacky at that point, just enough to drive the screen. And then we actually paired together to actually finish the porting process to get it to work with Scenic, because the earlier version of the Inky library to support the smaller Inky screens already had some of that there. But then more time passes. This time Jason Johnson has a kid, and then I find out that the Inky Impression 7.3 inch has been released, which is coming from the 5.7 inch. It's like, oh, this is so much larger, there's a lot more pixels, it just looks a lot better, and so I want to work with this in Elixir. So I started digging into that, but there were a few challenges along the way. One of the main challenges is that there is a completely new chip in this Inky compared to the 5.7 inch. So I had to dig into the datasheet for that chip and port out some more Python code. And another issue was an issue with the frame buffers, which I'll get into in a second. And the third is that the text rendering just looked pretty ugly and gnarly, which was also a problem on the previous one. So I port over all the code, and then I thought everything looked like it was correct, but then I render it here, and it does, it does not look correct. But there is sort of a, if you look at this, there is a pattern to what's happening here. It's not just completely random sets of dots. You can see there's very like sort of line-oriented things that's happening, and like all those little black dots is actually text that has been split across multiple lines. And if you look at the bottom, there's a suspicious area that's all completely empty, that's not being used or drawn to. So what's happening here is that the default Raspberry Pi frame buffer is only 720 by 480 pixels wide, whereas the Inky Impression is 800 by 480. So there is a full 80 by 40 pixels that are not addressable, and that was what was causing the smearing there. So why does the frame buffer even matter for this? So the way that the Scenic driver Inky works is that it uses the main Scenic library, which is the Scenic driver local, to actually draw to the frame buffer. And then, the Inky Scenic driver uses the RPI frame buffer capture library to read from that frame buffer as a RGB24 image, which is then trivially decoded into getting the individual colors of each pixel. And once it has the colors for the pixels, it sends that to the Inky library itself, which then takes that map of pixels to values and sends it over SPI, serial peripheral interface, to the actual Inky Impression hardware. So if there's something wrong with the frame buffer, then everything that follows from there will be all scrambled. So how do we solve this? Well, looking at the Pi docs, there's something called the frame buffer width and frame buffer height. And those control the width and the height of the frame buffer. So straightforward, right? No. Unfortunately, those configurations do, as far as I can tell, just don't do anything. I'm sure they worked on like a previous version of the Pis, maybe an earlier one before the RPI 0 that I have, but right now they do nothing. So I said, okay, maybe I'll try a more powerful Raspberry Pi. So I try Raspberry Pi 3, and I get a nice big frame buffer. Great. I clean up my code, I get ready to push up a PR, but then I come back the next day, and I'm getting everything all scrambled again. So what happened? What changed? Well, it turns out that I was using an HDMI monitor plugged into the Pi 3 because I was a full HDMI port, so I could see the output without waiting for that full 40-second refresh. And when you plug in an HDMI monitor, it actually changes the size of the frame buffer. So I got to thinking, I wonder if I can use that somehow. So I look in the RPI docs again, and I find a setting called HDMI edit file. And if you set that to 1, then you can basically pretend to the Pi that, oh, there is actually a HDMI monitor attached, so you should change your frame buffer size as a side effect. So how do we actually use that with nerves? OK, so to recap, our goal is to, in the config.txt, which is the Raspberry Pi bootloader configuration, we want to set HDMI edid file equals 1, which will tell the Pi to load our edid.dat file, which describes our monitor's information. So how do we actually set config.txt? Well, it's time to dig into FWUp, which is what Nerves uses to load and manage your firmware. So here's all the relevant files to help you keep them straight in your head. There's FWUp, which is the Nerves firmware config. There's config.txt, which is the Raspberry Pi bootloader configuration. And then there's the edid.dat file, which describes our HDMI monitor. So our first step is to copy the fwup.conf file from the Nerve system. So in this case, we're copying it from the Nerve system RPI0, and we're copying that into our own configuration directory of our Elixir application. And then we do the same thing for config.txt. And then we have to tell Nerves that we want to use our own fwup.conf rather than using the default from the system. And we do that by setting the Nerves firmware configuration inside of our Elixir configuration. Then we need to actually customize our config.txt to add the HDMI edid file equals 1. So just add that to the very end of the file. And I'd also recommend adding a few comments so you remember why you have that in the first place. And then you can go to fwup.conf, and now we need to tell fwup.conf, OK, we want to use our custom config.txt rather than the default. So in the file resource declaration for config.txt, we want to change the host path from pointing at the Nerve system to pointing into our own application inside our config directory. And now the next step will be to add edid.dat to our /boot directory. OK, looking at the Nerves doc, let's use this thing called rootfs overlay, which allows you to add files to any part of your Nerves system or firmware, except that doesn't allow you to add, that allows you to add files basically anywhere on your system except for /boot. So now we need to go back to fwup.conf. So our new goal here is we need to tell fwup.conf to add edid.dat to /boot because the Nerves fwup.conf is what is controlling what is added to that directory. So we need to create a new file resource for edid.dat, and we're pointing it into a Nerves app in our configuration directory. Then we have to further modify fwup.conf to modify the different tasks that are in there. So for example, this complete task, when this runs, we want our edid.dat file to be copied into that boot A partition. And then we need to do the same thing for our the upgrade A and upgrade B tasks. And that's necessary because Nerves uses 2 different firmware partitions so that if you break something, you can always revert back to the previous partition. And by adding this, this will copy our files into /boot when the firmware is built. So great, let's try it. And it works. So rather than a scrambled display, I have something that looks great. So now that we can support the 7.3-inch Inky impression, now I need to actually build the dashboard itself. So I have something to display. And here's what the display looks like. And shucks, demos. OK, and then I can at least show this part of the demo. So one of the cool things about e-ink, as I mentioned before, is that it does not need power. So if I disconnect the power from here, then I still have my full screen, although it's only showing the test code right now. Put that back. OK, on the left of my display, I have some information about my coworkers. I work with coworkers that are all over the, and this is also sample data. I don't actually get to work with Jose, but I work with people across many different time zones, from the West Coast to the East Coast to Argentina and also Spain. And it can be hard to remember what time it is for each person there. So I just want to be a little bit more connected and know what time it is for them so I don't interrupt them during like their lunch or dinner or what have you. And I also like to know the weather in their current locations. Up on the right, I have a quote of the day that changes every morning, just something that I want to remind myself of throughout the day. And I also have a calendar and the current time. And at the bottom left, I have the latest edition, which is a visualization of my Pomodoros that I do. This is what the back of the screen looks like. The Pi just connects directly into the back there and just hangs off. To put it on the stand, I just added a few pieces of cork to keep the Pi from touching the back of the stand, because that would probably be bad for the electrical system there. Here's all the pieces, and let's dig into a few of them. So here is a close-up of the coworker view. So I have their person's name and location. I have the current weather. And for the temperature, I have it in both Fahrenheit and Celsius because I'm trying to learn and internalize Celsius because it's better. And I have a little indicator that gives me an idea if that person is probably working based on their current time and schedule. And then I also have information about how many PRs they have up that need review from someone else, as well as how many PRs that are up that they need to review themselves. Here's an example of some of the quotes that I'm trying to internalize. I really like this quote from Joe Armstrong. And here is the Pomodoro visualization. So each Pomodoro is made up of 3 different rectangles. There's, I guess, about 6 shown here. The first rectangle is actually the red rectangle, and then orange is the limbo time, and then blue is the rest. And if you don't remember what Pomodoro is, usually you work for like 30 minutes, then you take a break for 5 minutes. So as you can tell by how long this limbo section that I've added in my own version of Pomodoro is a lot longer than 30 minutes. So I have not been sticking to a strict schedule, but it's nice to be able to see it visually represented like this. And then this is all sitting on top of a long line, that rectangle there. And that represents the time from when I would start the day to potentially finishing it. And I also have a little mark for 12 o'clock noon in the middle there, and another red mark for the current time. And here is the network architecture for my dashboard. So I have the ink dash in the middle here, and it gets the GitHub statistics from a separate application that I run on my personal server that's talking to GitHub. And then I get the weather information from a service called Pirate Weather. So if you remember Dark Sky, which I was really sad that it got shut down, Pirate Weather is completely API compatible with the Dark Sky API. And they have a generous free tier, and I also donate to support them because I really like what they do. I store my quotes on Trello so that I can update them easily without having to push new firmware to my device. And to get my Pomodoro stats, I added a small Phoenix app to the Scenic side screen that I talked about a couple years ago at ElixirConf that I'm able to fetch Pomodoro info over HTTP. And this is all powered from my personal desktop, which is used for flashing firmware. It uses a single USB cable for flashing firmware, along with providing power and providing network connectivity to the device. Here's the process architecture for the server. There's a couple gen servers to handle button presses, and there's a gen server that's handling the weather. So it's what fetches the weather and stores a cache of it. And similarly, the Pomodoro server is storing a cache of the Pomodoros. And then I'm using the quantum library to orchestrate all this and control when things happen at individual times. So this is what the quantum configuration looks like. I set my time zone so that I can set things in my time zone instead of having to convert everything to UTC. So I update the weather at every 29 and 59 minute mark, but only from 5 a.m. to 10 p.m. There's no reason to be refreshing the display when I'm not going to be looking at it. And it also cuts down on energy usage and my API credits. But for the Pomodoros, I'm fetching them every minute. And then for the home screen, this is one of the most important lines, the third one down here. It refreshes the screen every 30 minutes. Because of the long refresh time, I don't want to refresh it more often than that. It would just end up being a little bit more distracting. So the other challenge that I was mentioning is the font rendering looks ugly. So by default, when I first started up this project, this is what text would look like. And this should just be plain black and white text, but it ends up with like all these little jagged things sticking out of the N and even some green coloring as well. So let's talk about making that beautiful. So first we need to dig into why that's happening. And the reason for that is something called subpixel hinting. So subpixel hinting, rather than having pixels be just completely black or white, it has different colors of gray, as well as adding in some color to kind of fake your eyes when text is small, to make it look like it's like a nice curve, even though it's made up of these individual pixels. But we want to completely avoid this for our work here. So how do we do that? So we do that by using a pixel font. So if you look at this Minecraft font on the left here, I'm trying different font sizes, and it looks really good at sizes 10 and sizes 20. But at any other size, it also ends up with like these jagged features. So what you want is to use a pixel font at the correct font size or multiple other font size that it's meant to. And by doing that, you can turn something very jagged like this on the left into something that looks great on the right here. OK, and let's talk about how I use Scenic in this application. So one of the things to know when you're using Scenic is that by default, you'll be doing a lot of absolute positioning. So these are all the coordinates for the major components in my main scene with Scenic here. So very different than when you're working with the web, but it's actually kind of refreshing. You don't have to worry about any responsive design and how things will look at different sort of viewports. Instead, OK, my screen is always going to be 800 by 480, and you position things around that. And here's another view of the Pomodoro again. So each Pomodoro is made up of those 3 different rectangles I mentioned. So there's the red rectangle for the work time, orange for the limbo, and then blue for the rest time. And this is how you would render them with Scenic. You can think of each major function in Scenic as returning a graph data structure that represents all the shapes that you want to display in your scene or in your component. And so we start by creating a new graph, and we add that initial rectangle below it, which is the line that represents the whole time span from the beginning to your end of the day. And then in order to find out where each of these rectangles should start, I use a library called context, which is a SVG library in Elixir. And for the domain, I'm passing it 6 and 18 to represent 6 a.m. and 6 p.m. because that's generally I'm starting and working within those sort of time frames. And the range is whatever the full width is on the screen. And then to render each Pomodoro, we take in that initial graph, and we're adding to it multiple rectangles. So first, we're adding the blue or the red work rectangle, and that's going from whenever we started the Pomodoro to whenever the Pomodoro main time was finished. And then we have the orange limbo rectangle, which is going from the Pomodoro finish time to whenever I started to rest. And then lastly, the blue rest rectangle, which is going from when I started the rest to whenever I finished the rest. And then we also add those little marks I mentioned. So we add the 12 o'clock of rectangle for that. And that rectangle is 2 pixels wide by 10 pixels tall. And we pass it as the start position 12 o'clock noon, and then 10 pixels down, so it's the rest below that initial line. And then the last one is the current time rectangle, which is the little red mark that's going at whatever the current time is. And these are the functions that power that. So to draw the rectangle, you have a little bit of error checking to make sure you have an actual start and finish time. And then you have the start position and the finish position. And those are you pass in the start time and the finish time into the scale function, and it gives you back a x position within that time range. And then to get the width, you just subtract that finish position from the start position, and then you create a rectangle that has the width of that, width, and it starts at that x position, and you give it the fill of whatever color it is, red, orange, or blue. And if you're developing in Scenic and Nerves with e-ink, I have a few tips for you. First is I would recommend using Pi 3 instead of a Pi 0 when you're doing your development. It's roughly like 3 times faster. So every time you're pushing new firmware or booting, it's just so much faster. And additionally, lowering your iteration speed, I recommend using a HDMI display so you can see what your screen will display before that full 40-second refresh time. But even faster than that, you can develop in host mode, so that is on your main computer. And if you're doing that, you can actually use my Scenic Live Reload project, and you can get changes that'll happen a few seconds after you make a change in your editor, instead of having to stop and start Scenic to see the change. And if you want some pre-made components, there's a few of us that have started creating some Scenic contrib components that have some shared patterns and components that you can use. So I really love having my e-ink dash on my screen. It gives me a great visibility into my day and information about my coworkers and what they're up to. And you could have one as well. So thank you.